This is section 14.4 for Algebra 2 Trig, the geometry of complex numbers. How do we plot complex numbers in the complex plane? Yes, you can plot complex numbers. No, it's really not that bad, so don't get all worried. How do we use the polar form of complex numbers? So if you remember back whenever we studied complex numbers, that complex numbers are written in the form a plus bi, where a is the rational part or the real part, and b is the imaginary part. A and b are real numbers, and I squared equals -1. We can also represent complex numbers in the coordinate plane using the format x plus yi, where x and y are real numbers, and they correspond to the ordered pair, the coordinates x comma y. So you would basically plot x like you would x and y as you would y. So you would just rewrite the numbers as x plus yi instead of a plus bi. The complex plane is when the coordinate plane is used to plot a complex number. The horizontal axis is called the real axis because you're going to plot the real part of the number on the x direction. The vertical axis, or the y direction, is the imaginary axis. It's going to represent the coefficient for I. So let's call z x plus yi. So z we're going to represent as a complex number. Geometrically, the absolute value of z, square root of x squared plus y squared, is the distance from the origin to the point z. So the origin 0, 0 to the point z, where the absolute value of z is the magnitude of the vector oz. So don't worry about the vector part. We didn't get into it in the earlier part of chapter 14. Basically, what you just need to note is that the absolute value of z is the distance from the origin to point z, which are the coordinates of the complex number. The conjugate of z, remember z is x plus yi, is x minus yi. So you will see the conjugate denoted by this little line on top of the z. The negative of z is negative x minus yi. So the conjugate is basically flipping the sign for y, so x minus yi. The negative of z is negating both the real part and the imaginary part of the complex number. So the graph of z. The graph of z is basically like plotting any ordered pair. You're going to plot x comma y in the coordinate plane. Remember, the distance or the magnitude of z, they call it the magnitude, is the distance from the origin to this point, and it's represented by the absolute value of z, which is the square root of x squared plus y squared. You're basically doing a Pythagorean theorem to get the distance. Now, if you wanted to graph the conjugate of x plus yi, it would be graphing x minus yi. So the x coordinate is the same, but the y coordinate is reflected over the x-axis. So if it was up here to begin with, the conjugate's going to be down here. If it started down here, it would be reflected up there. And the negative of z would be negative x minus y. Notice that it's basically a reflection around the line y equals, in this case, negative x, or it's a rotation 180 degrees around the origin. Now, to add two complex numbers is pretty simple. It's basically just like when we did before. You're going to add the exponents and add the y components. Example 1. Plot w equals -2 plus 3i, z equals 2 plus 2i, w plus z, and w minus z in the same complex plane. Alright, why don't you guys give this a shot? To add w and z, you just add the real and the imaginary parts together, and same when you subtract. Alright, so I've color-coded each one. So let's start with w. W is -2 plus 3i, so that goes here. Yes, you're going to want to draw the segment from the origin to point w. Z is at 2 plus 2i, so it's going to be graphed at 2 comma 2, so this represents z. W plus z, you just add the two complex numbers together and you get 5i, so it's 0 for x, 5 for y. So that segment, this point, is w plus z. Finally, for w minus z, if you subtract it, you get -4 plus I. So that means you're going to graph -4 comma 1. So this represents w minus z. So when you graph complex numbers in the coordinate plane, you are going to not just plot the point, but also graph the distance, so you know how long it is from the origin to that point. You can express the real and imaginary parts of the complex number z equals x plus yi in terms of its distance and direction from the origin. So basically we're going to convert this from a rectangular coordinate to polar coordinates. So the vector oz, which is basically from here to point z, has a length r and it also makes an angle with a positive real axis. So this was the polar axis. This is the initial side when we did angles in the coordinate plane. So you can represent point Z this way: x equals r cosine theta, y equals r sine theta. So the complex number z equals x plus yi can be written as z equals x, which is r cosine theta, plus yi, substitute in r sine theta for y. So if you expand that or factor out an r, you get z equaling r times the quantity cosine theta plus I sine theta. And this is going to be the general form for a complex number using polar coordinates. So once again, the polar or trigonometric form of a non-zero complex number z equals x plus yi is given by z equals r times the quantity cosine theta plus I sine theta, where r is equal to the square root of x squared plus y squared, which is the same thing that we did in section 4.3. And theta is an angle such that cosine theta is x over r and sine theta equals y over r. So nothing new here. We're just rewriting a complex number using polar form, where x is cosine theta, x is r cosine theta, y is r sine theta. Factor out the r, and this is where these numbers come from. So the angle theta here is called the amplitude or argument of z. So here theta will be such that theta is between 0 and 360, or 0 inclusive but excluding 360. So when we write out numbers, we're going to choose a number from 0 to 360. And if it's over 360, you could always use the coterminal angle that is between 0 and 360. The absolute value, r equals the absolute value of z, is sometimes called the modulus of z. Now I'm not going to ask you questions on this because you don't necessarily need to know what it's called or what it means. You just need to know how to solve the problems and what each letter represents in the coordinate plane. You don't have to know the name of it. I'm not too concerned about that. But I would like you to be able to represent these and have a graphic image of what you're actually solving for. Example 2a, express negative 4 plus 3i in polar form. Leave the amplitude to the nearest tenth of a degree. So let's go ahead and do this one. So there is negative 4 plus 3i on the coordinate plane. So the first step to doing this is you have to find r. So to find r, you're going to use the equation r equals the square root of x squared plus y squared. Well, we know what x is, it's negative 4. We know what y is, it's 3. So if you plug those in, and remember in this case r is generally going to be positive, it's going to be positive basically, r is going to equal 5. So now you have r. Now you need to find theta. Now, to solve for theta, you can choose either cosine or sine. It doesn't matter which. Just remember, your theta should be in the second quadrant because the coordinate of your point is in the second quadrant. So your theta really should be between 90 and 180. So, if we use sine, sine is y over r. So that's 3 over 5 or 0.6, which means you will get a reference angle of, I'm going to guess, 36.9 degrees. But don't forget you need to find the second quadrant angle because your coordinate is in the second quadrant, which means theta is going to be between 90 and 180. So the answer here is 143.1 degrees. So you have your r, you have your theta. Now you put that all together. Your negative 4 plus 3i equals r, which is 5, times cosine theta plus I sine theta. So 5 times cosine, 143.1 degrees, plus I sine, 143.1 degrees. And in polar form, you will notice theta is going to be the same because it appears both after the sine and the cosine. So when you see a problem where you're converting a complex number to polar form, first solve for r, use either sine or cosine to solve for theta. Remember, taking note which quadrant theta is in. You're going to get the reference angle if you use your calculator. Then use that reference angle to calculate the angle in the correct quadrant. 2b, express w equals 3 cosine 135 plus I sine 135 in x plus yi form. So now we're just going to go backwards. So there's 135 degrees. It's halfway between 90 and 180. And I will tell you this is not going to be 3 units from the center, but we'll see how it works. So solve for x and y using r cosine theta for x and then r sine theta for y. So x is r cosine theta, which is 3 cosine 135. So that turns out to be negative 3 radical 2 over 2 because cosine 135 is negative root 2 over 2 in the second quadrant. For y, you're going to plug in 3 sine 135. And in this case, sine of 135 is positive because y is positive in the second quadrant. So y is 3 radical 2 over 2. So now we have your x and your y. All you have to do is put them in complex form. So 3 cosine 135 plus I sine 135 is equal to negative 3 radical 2 over 2 plus 3 radical 2 over 2i. Now remember, when you get your complex number, make sure that the signs match the correct quadrant. If you're in quadrant 2, your x must be negative and your y must be positive. So make sure you double check that. I hate to see you lose points because you just did not inspect which quadrant your complex number was in based on the signs of x and y. Finally, multiplying and dividing complex numbers. To multiply two complex numbers, multiply their absolute values and add their amplitudes. To divide two complex numbers, divide their absolute values and subtract their amplitudes. Now you can see how this looks in formula form. If W is A cosine alpha plus I sine alpha and Z equals B cosine beta plus I sine beta, then the product of W and Z, you're going to multiply the two R values. WZ equals AB times the quantity cosine of the sum of the angles plus I sine the sum of the angles. If you're dividing W divided by Z, you're going to divide the R values. So A divided by B times the quantity cosine alpha minus beta plus I sine alpha minus beta. So notice again, when you're multiplying two complex numbers in polar form, you're going to first multiply their magnitudes or amplitudes, and then you're going to add the angles together for both cosine and sine. To divide, you're going to divide their amplitudes, and then you're going to subtract the second angle from the first. So write those down, and let's use them to solve example 3. Let W equal 3 times cosine 35 plus I sine 35, and Z equals 1.6 cosine 80 plus I sine 80. Let's find WZ and W over Z. So let's apply the formulas that we just learned. So WZ is the product of A and B times the quantity of the cosine of the sum plus I sine of the sum. So let's plug those in. A times B is 3 times 1.6 cosine of 35 plus 80 plus I sine 35 plus 80. 3 times 1.6 is 4.8. 35 plus 80 is 115. So your product is 4.8 times the cosine of 115 plus I sine 115. So multiplying them is just simply multiplying the R values and then adding the angles together for both cosine and sine. To find W divided by Z, we're going to use this formula. Remember, you're going to divide the R values and then subtract the angles from each other. So let's plug those in. W over Z is 3 over 1.6 times the cosine of 35 minus 80 plus I sine 35 minus 80. Now, you get 1.875 cosine negative 45 plus I sine negative 45. But remember, in polar form, theta must be between 0 and 360. So you're going to have to find that angle that's coterminal with negative 45. So if you added 360 to this, you will get 315. So your final answer is 1.875 times the cosine of 315 plus I sine 315. That's it for section 14.4. It's just a matter of plotting some points, being able to convert from polar form to complex form, and being able to multiply and divide complex numbers in polar form. If you have any questions, please email me or ask me during class.